All right, folks, I think I'm going to start up here. All right, so I'd like to welcome everyone to this Water Institute Water Talk here at the University of Waterloo. It is very much my pleasure to introduce today's speaker, Dr. David Steward of North Dakota State University. Dr. Steward is the Walter B. Booth Distinguished Professor at NDSU. He is a fellow of the American Society of Civil Engineers, and he is a recent chair of the Department of Civil Construction and Environmental Engineering at that university. Dr. Steward did his PhD at the University of Minnesota, working with the founder of the analytic element method, Dr. Otto Strauch. He has spent much of his career at Kansas State University, where he's been working in interdisciplinary studies of water resources, but also spending a good deal of time and publishing extensively on the analytic element method, both developing mathematical improvements to the method and applying it to new fields to which it hadn't been applied to before. This work has kind of culminated to a recent publication of a book on the analytic element method, which I think he's going to be addressing a bit in his talk, which we're looking forward to here. So Julie, could you go to the next slide here? Before we proceed, I just want to acknowledge that the University of Waterloo, who's hosting this talk, is located on the Haldeman Tract, which is land promised to the Six Nations in the Treaty of 1784. That tract extends 6 miles on either side of the Grand River. At this point, I'd like to pass it over to you, Dr. Steward, and I will say I'm very much looking forward to your talk today.
Very good. I should have the screen share.
I will note one more thing, that this talk will be recorded.
Very good. Thank you, Dr. Craig. It's a great pleasure to be able to visit with you today and share some of the new things that are going on in the analytic element method. I know that we're going to be, we have some applied mathematicians in the audience, and the methods that we use for the analytic element method I'll kind of highlight about halfway through the talk. They're fairly simple mathematical solutions, but they've been brought together in new ways that allow us to be able to achieve solutions that we have not previously been able to achieve. As Dr. Craig said, there's a number of new fields that the analytic element method has been applied to, and also highlight a lot of those advances as well. Before I get started, I'd like to just kind of show you the book here, the Analytic Element Method, Complex Interactions of Boundaries and Interfaces. This is a book that I published about a year ago with Oxford University Press, and it brings together the methods that I've been using with my colleagues over the last few decades, and kind of puts it together in a way that is easy, I hope, for people to pick up. And before I go through and show you some of the examples, I'm just going to jump out of here. If you're on a computer, and if you want to open up your computer to a web browser, I'm going to jump out here for just a second. And I'm going to I'll use Google, and I'm just going to put in AEM, Analytic Element Method, and my last name, Steward. If you are not at a web browser, you can go back and do this again at any of your computers. The first thing that pops up on my computer here is Analytic Element Method, globaloup.com. And if I click on that link, that's the link to the book. And the reason I wanted to show you this is not so much for the book right now, but for the companion site. So there's a companion website available. When I worked through the contract with Oxford, I wanted quite a bit of the book to be available for free, so that people could kind of get a flavor of what the analytic element method is, so it could be broadly distributed, and people could kind of see, is this something that I would want to use in the studies that I'm working on? Is it something that I would want to use? And so right here, the supplementary material contains the first chapter in section 2.1. I'm going to take you through that a little bit later. So you don't have to worry about going through it right now, but I'll take you through that in a little bit. And it also has supplementary material right here. It's a zip file. The second version of it is out there right now. I'll be updating it again fairly soon with some more material, but approximately the first half, or almost 2/3 of the book, the figures that are in the book have been implemented, and I'll show you how to use the software to be able to learn the methods along with the presentation of the book. I'm going to go back now, and if you are at this site, please don't spend the next half hour going or 20 minutes going through the material. Instead, if you could come back and stay with me for just a little bit. What I'm going to do is I'll take you through and show you, here we go. I'm going to show you some examples of the analytic element method and what kind of things we can do with the analytic element method. It started in the groundwater world, and so a lot of these examples have bearing to groundwater. I'll show you some examples for wells, so I'll just kind of use my pointer here to take you around the circle. Wells, groundwater surface water interactions, phreatophytes, so these are plants that can pull water up from the ground, cracks and fissures, heterogeneities, and Virosome flow, so flow recharge down through the Virosome, and then waves. So I was a coastal engineer for a year at the University of Maine as a postdoc and picked that up there. And I also wanted to kind of shout out that you have one of the lead analytic element method people working in your institute as well at Waterloo. James Craig has written a number of excellent articles, and he wrote computer code Visual AEM, which I use to teach my classes, and I know is being used to teach groundwater classes really throughout the world. So shout out to James and the methods that he's promoting through the education of Visual AEM at University of Waterloo. So how does the analytic element method work, or how do we use it to model things? Well, let's start with a well. If we look at a well from up above, if we look from straight down, it looks like a point on a map. When we are trying to model what's going on around a well, we specify boundary conditions. So this is kind of like the way we visualize the world with analytic elements. We look at things in terms of their geometry, how they interact with the world, and what kind of mathematical functions we need to be able to interact with the world. So it looks like a point. We typically will specify pumping rate, so how much water is being pulled out of an aquifer. And we have some fairly standard mathematical functions that we use to be able to model those. The team solution for steady well and tie solution for well drawdown. The team solution gives you something that looks like this. These lines are given groundwater head or groundwater elevation. The arrows point in the direction of groundwater flow. So this is the steady flow of water if it's been turned on for a long time. That's the team solution. The tie solution starts with an initial flat plane and looks at the cone of depression as it progresses over time. The kind of things that we can do with these at the analytic element method, and I'll show you this example. This is the first one I'll show you of the example code. We have 3 wells, and they have pumping rates. There's a regional gradient that's trying to drive the flow past the wells. These black lines are lines of constant groundwater elevation. The flow goes in the direction of the arrows. The white lines are the stream lines, so they're the trajectories of the groundwater particles. And we can see by looking at the stream lines that some of the groundwater particles end at this well, some end at this well, some flow between the wells. So these solutions that we have with the analytic element method for wells, they allow us to be able to look at things like capture zones and where do we need to protect water, where do we need to protect land use to be able to make sure we have clean drinking water. So that's an analytic element method solution for a well. Next on the list is groundwater surface water interaction. And when we look at groundwater from up above, it looks like a line. We have different kinds of boundary conditions. Sometimes we'll specify the elevation of the river. Sometimes we'll specify that the bed has a certain resistance, and so it's holding that water up away from the aquifer. We have different ways of being able to model this. Wells and line sinks are all in Visual AEM. So if you want to play with some code that's really has a nice interface, Visual AEM is there. This is an example of a couple of different kinds of lines that we can use. These are curved lines. So this is a Bezier curve and a B-spline. These are the curves that are used in ArcGIS and in PowerPoint. And this is just an example of a small piece of a river that's separated from the groundwater. So the head is not constant along the river, but instead there's a resisting layer in the bottom that's holding that water up. The kind of things that we can look at with these, this is an example of a river network. So there's a river network. This comes from a paper that we published in Water Resources Research a few years ago. And this is a river network. what we did is artificially, we allowed the head to increase by an increment of 1 along every stream reach. Not that that's physically what's going on, but just to be able to visualize how accurate the model is. This area here is blown up by a factor of 100, so it's, and then this area here is blown up by a factor of 100. And you can see that these lines of constant elevation, they're specified to be linear along each line, and we match the specified boundary conditions very accurately. In fact, with this solution, we matched the groundwater elevation at each one of the control points that we specify along these lines to six to 8 significant digits. That's fairly typical. So we have an extremely accurate solution of a river network. We could have blown up into any one of these sections of the river and we would have gotten the exact same level of detail. So it's an extremely accurate solution. If you have seen analytic element method before, this is very familiar to. If you have not seen analytic element method, it's just an extremely accurate method to be able to analyze groundwater flow patterns. The mathematics behind it are single layers, and I won't go through that right now. Just, that's the kind of mathematical functions they are. So here's our example of the stream network. Next, phreatophytes. And so phreatophytes, when you look at it from up above, it looks like, in this case, a circle. We're just drawing a circle around the canopy of the tree or the root area. We have a specified extraction. So this kind of looks like a well. It's taking the water out along the top of an aquifer, and from a ways away, it looks like a well. We can have fields of phreatophytes that withdraw water, and so they pull up water collectively as a field. And the solutions here, they're solutions to the Poisson equation. This is an example of a capture zone. So this is the kind of thing you can do with analytic elements. This is a capture zone. Instead of the capture zone for a well that I showed you just a moment ago, this is a capture zone for an individual tree. And so this is a view from looking above. So this is the canopy of the tree or the root area of the tree. Groundwater is the regional gradient of groundwater is trying to drive the flow past the well. If we kind of draw a line straight through there and look at a section view, in this particular part of Kansas, we know that from doing isotope analysis that the amount of water being brought up in the tree averages out to about 8 times more than the regional recharge that's occurring in the area. And so there's 8 times more extraction than there is recharge. And so when we look at groundwater particles beneath the tree, they're trying to be driven past the tree, but they're being drawn up by the roots. Further away from the tree, we have water particles with the recharge occurring on top of those. And if we trace particles around this tree backwards in time, we get kind of a 3-dimensional visualization of a capture zone for a phreatophyte, a capture zone for a tree. And this particular figure here, if we look at the capture zones for a set of trees, Trevor Ehring worked on this with me, and we depicted a couple thousand cottonwood trees and looked at the individual capture zones. And once again, kind of like this individual tree, the capture zone, the wells or the path lines, as you go backwards in time, they go down beneath the trees and then they come back up when there's no trees there. So we get these funny path lines. If you trace them forward, they'll end up at these individual trees. In complicated geometries of capture zones for trees. And so there's an analytic element method solution for trees. Next is heterogeneities. And so heterogeneities can look like a line, or it can look like an area, like a polygon. We have a variety of different kind of boundary conditions we can apply to these, different kinds of mathematical functions that we can apply. This particular example is flow that looks like a fracture, where water is coming into one end, flowing along the fracture, and flowing back out into the aquifer on the other end of the fracture. Here's a set of linked fractures. Here is a heterogeneity. This is kind of like a sand with a coarse sand or a gravel inclusion, and it draws the water. and the water moves more quickly through. You can see the arrows are larger. It moves more through the heterogeneity. We can also have, and I'm going to come back to this example of a gravel inside of a fine sand or a sand just a little bit later on in the Virosome also. We can also have different boundary conditions. This is a boundary condition that tries to make the water flow around the element. So you could think of this as being like a sheet pile where the water's flowing around it. Here's a set of 500 elements that are impermeable, and the water is trying to flow around and all these elements. There's, like I said, there's 500 elements here. You could view this as a set of clay lenses of kind of semi-arbitrary orientation that are interacting very closely with one another to make the water flow in or flow through the various passages between the elements. This is an analytic element method solution that we published a slit element in Water Resources Research a few years ago, and I don't think there's any other numerical methods, at least none to my knowledge, that can match the kind of detailed depictions that you get of the infinite flows at the ends, the infinite velocities, and the close interactions of these elements. So that's heterogeneities. Next is the Virosome. And so in the Virosome, recharge tries to go down until it hits groundwater. This depicts a set of heterogeneities that kind of look like circles. So we can have gravel, or we can have silts inside of a fine sand. And this depicts a silt inhomogeneity inside of a fine sand. It has a set of boundary conditions. Pressure head, which is these darker lines, this is pressure head, is continuous across every one of these interfaces. Also, all the flow that goes into the interface has to come into the element, so it matches a continuity of flow and a conservation of mass. Conservation of mass and a conservation of energy boundary conditions. And this particular element is located down here close to the water surface. This is groundwater, and this is located further up in the Virosome. So we know in the Virosome that the pressure head becomes negative as you go up in the water or in the soil column, and this element is further up in the soil column above the water table. This is a coarse sand inside of a fine sand, and so this is like the heterogeneity that I showed you in groundwater just a little bit ago. I just kind of as a heads up here, I'm going to take a couple minutes to take any questions you have in about 3 more slides. So if you've got questions about any of these particular examples, I'll take some questions. And then after a few questions, then I'm going to go on and show you how these methods actually work, how we can implement them. So this is a kind of like a coarse sand inside of a fine sand. This is down here at the water table. And if I go back again, a couple of slides just to show you, in groundwater, gravel draws water. In the Virosome, if you're down close to the water table, gravel draws the water as well. Flow flows through the heterogeneity. Boy, that's a tongue twister. More readily in the gravel than it does out in the sand. But as you get further up in the water column, the gravel actually repels the water. The water flows around it because of the saturated conductivity relationship. It's a nonlinear relationship. And as you get a drier or a lower negative pressure, the gravel dries up more quickly than a fine sand does. So it's just an interesting artifact that you learn from these kind of analytic solutions, the way that the recharge is behaving in nature. The last example that I'll show you comes from coastal engineering, and we have different types of geometries we can look at there. These are a little bit more complicated because the boundary conditions are actually complex. There's a real and an imaginary part. We have Hilbert conditions that incorporate those. There are also solutions to the Helmholtz equation. So the mathematics, again, is a little bit different mathematical equation. The solutions, this is an impermeable object. So you could think of it as an island that the long waves are moving past. or you could think of it as a bridge pier that the waves are moving past. This just shows the interaction of a lot of different impermeable objects, or fully reflecting objects, I guess I should say. And this top set of panels here shows the amplitude. So if we have waves, and if we look at the height of a wave above the mean sea level, that's the amplitude. So this gives us a depiction of the height of waves. This particular example has partially standing waves, because some areas the waves are bigger and some areas the waves are smaller than they would be out in the open sea. We also visualize those using the phase. The phase is white at the top of a wave and dark at the bottom of a wave, white at the top of a wave, so we can see the top of the wave, the bottom, the trough, the crest of the waves. And so the phase and the amplitude together allow us to get a depiction of how waves are moving through a field. In order to match the boundary conditions, these lines of constant amplitude and lines of constant phase should intersect the boundary at 90 degrees, and they do. So once again, we have a very accurate depiction. This was published in ASE Journal of Ports in 2018, and this is the first analytic element method solution of coastal engineering. We extended that with the paper, or I guess I should say I did. I think I was the only author on that one. We extended it in 2020 to waves moving through objects. And so this is waves moving across shoals, across an area that has a shallower water depth. In shallower water, the waves get closer together and their amplitude increases. And this is waves moving across troughs, so depressions in the bottom of the ocean. And once again, these lines should be intersecting, or they should be continuous across the interfaces, and lines of constant phase should be continuous as well. So we have an extremely accurate solution of analytic element method. This particular type of a model is used to look at not only depressions and shoals, or depressions in shoals, but also to look at vegetative matter. There's been a number of papers published in the last 5 years or so that have looked at waves as they move through vegetation in coastal regions, and how the wavelengths are changed within those. This is the first paper that publishes solutions with more than one vegetative patch using the analytic element method. So the other methods, it extends the existing methodology that we have today. And this is just a depiction of a tsunami length wave, so something a period about 5 minutes moving across deep water shoals, and the amplification on the backside of the set of shoals and tsunami waves. So I'm going to take just a real quick break here. James, are there any questions out there that the people have at this particular moment?
There are no questions in the Q&A right now, Dave.
Okay, very good. Then I will go ahead and kind of go through the. So I'm going to take a kind of a quick step back here. Analytic element method allows us to be able to develop very accurate solutions of a very wide range of problems that are of interest to us in the water world. These examples also have counterparts in other fields, and I'm going to show you that in just a second. So here I will get out of the presentation here, and I'm going to go to. This is a copy of the PDF that's available for you at the web page. This is the full book, so it has a little bit more than the version that's out there, but you will have basically pages 1 through pages 79, I think. In the analytic element method, there's a number of fields of study that analytic element method has been explained to. So we take the mathematics that exist, basically the mathematics that were developed up through like about the 1960s or so for all these different fields. And I can give you an example that water, the waves, let me actually go back here. The waves moving or reflecting off of one island, that was published by HOMA in the Shore Protection Manual back in the 1950s. And we have very similar, Sommerfeld published similar types of solutions for electromagnetic waves. So these theories and the foundation of the analytic element method, the actual mathematics, were put together by mathematicians and engineers up through about the 1960s or so. And they were able to look at something like this, where you have waves reflecting off of one island. But they were not able to go forward and figure out how these elements interact with one another, and how the waves reflecting off of one island interact with the waves reflecting off of other islands, or how the waves moving across one shoal impact the lee side shoals, or the ones that are closer to the open sea. And so they were not able to do that because they didn't have the computational capacity to be able to solve those equations. And that led to us developing a set of techniques that would solve those when we got computers, finite elements and finite differences. And that's really where most of the field has gone, is in the finite element and finite differences methods. But just as the computer has allowed us to be able to take those finite techniques and implement them in new ways, the computers have also allowed us to be able to take the groundwater type solutions that we had, the exact same things, the analytic solutions, and apply them in brand new ways to look at things like these river networks. And so there's a lot of powerful mathematics that were developed through the 1960s or so that we kind of forgot about. And there's been kind of a renewed interest in people to come back and revisit some of those methods. And the analytic element method gives you a really powerful way to be able to bring those together. So there's each one of these examples here: groundwater flow. Let me blow this up for you. Groundwater flow, Virosome flow, incompressible flow. So this is things like flow over airplane wings, thermal conduction. So this is heat flow, electrostatics, looking at voltage and currents, water waves and acoustics, elasticity, looking at stress-strain relationships. The governing equations from these different fields are all pulled together in ways that the analytic element method can utilize. And then a set of examples for those different fields are shown. Where I'm going to take you right now is this analytic element method paradigm. There's just the analytic element method is very simple. So for those of you that in the applied mathematics region, this will be familiar to you, and it provides kind of the foundation for how it is that we solve things with the analytic element method. And I will see if I can. There we go. I'm going to have to make this just a little bit smaller to be able to show it to you. So there's really
Dave, can I just interrupt for a second? It's James here.
Yeah, sure.
There is a question in the chat here, but I don't know if you want me to see whether or not these should be answered during the talk or left for later, or what do you want to do here?
Well, I'll tell you what, why don't I go for about 3 more minutes and I'll take questions, okay?
All right, sounds good.
And then I'll show you the code after I've taken whatever questions are out there, okay?
All right.
So anybody that has questions about what it is that I've shown thus far, I would be delighted to take any questions. So the paradigm, there's really just 4 steps. Partitioning the domain into elements, that's kind of what I was showing you about those points, lines, polygons, the different types of elements, curved lines, straight lines, however we depict it. We develop a set of mathematical functions. This is really based upon what I told you that occurred through the 1960s or so. Boundary conditions are prescribed, and we solve these boundary conditions by adjusting coefficients. This too is done through the 1960s or so for individual elements. But then in the analytic element method, we develop comprehensive solutions that provide the influence functions for all elements. So we take everything a step further than what we've been able to thus far with the mathematics. So elements, they can take on the geometry of the outside of a circle, inside of a rectangle, an interface across a line. And then we bring together the mathematics of the discipline in one of kind of the amenable mathematical forms that we have using the Laplacian operator. I'm going to have to move this screen so I can take you through this a little bit better. Laplace equation, Poisson, Helmholtz, modified Helmholtz, biharmonic heat, and wave equations. So these are kind of the classic formulations that we have. Next, we develop a set of linear superposition of functions. And I'll show you some examples here. Here's a circle element. And we have a coefficient that's multiplied by a function. This is a very simple function. It just has a value of 0 inside and 1 outside. This is a little bit more complicated function. Here it has 1 on this point, -1 on that point, and kind of the flow goes from +1 to -1. Here we have something where it has +1 and -1, so it flows this way. The next, that's multiplied by a coefficient. The next element would go from +1 to -1 to +1 to -1. And you can think about this, you go up to a 20th order coefficient times a coefficient times a 20th order function. It'll go from +1 to -1 to +1 to -1 20 times around that circle. So we develop these series of influence functions that allow some variation around an element so we can match our boundary conditions. So this is a Laplacian type of a flow. We can do that for waves also. Here is this is a Bessel function. This is the amplitude. So here waves are moving away from the object. Here waves are moving away from it on this side and away from it on this side. Here waves are moving away from it on this side and away from it on this side. We match a Sommerfeld boundary condition or interface condition, so waves have to go away from the object. They can't go into the object. The next one here would have waves going out, 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 and so forth. So we allow a variation of waves going away from an object. Another example here is for stress strain. And so here we have compression on this side, tension on this side, compression on this side, tension, compression, tension, compression, tension, compression, tension, compression. So we bring together all these elements in ways that are all these functions that allow some variation around the outside of the element. And then we say, okay, element, you figure out how to solve for all those coefficients so you can match a boundary condition. You could say, well, I know the displacement around this boundary. Well, I know the traction. I know the stress around this boundary. Well, I know that this has to fully reflect the waves. So whatever your boundary condition is, you put together a series of equations where you multiply the coefficients times the functions evaluated at a point has to match whatever your boundary condition is. Given groundwater elevation, given temperature, given voltage, whatever it happens to be. We specify a set of control points that allows us to be able to develop a system of equations where we have coefficients times, we have a matrix that's evaluated functions times the coefficients to match our boundary condition. Now, this was done back through the 1950s, 1960s in a lot of different fields. There's a lot of different ways you can solve this. Sometimes we can simplify the Fourier coefficients. Sometimes we can use a Chebyshev formulation to be able to simplify the matrix. But one way or another, we've been able to solve that. What the analytic element method does is it says, okay, well, we know how to do this for one element. Now let's take that one element, what we're trying to solve for that one element, and take everything else in the world and call it an additional function. So all the other coefficients for all the other analytic elements are in that additional function, and the setting. So the regional flow, the overburden compression that we get from the soils above us, whatever the regional setting is, that goes outside of the element. So then the element only solves for the coefficients of itself. And then we say, okay, well, element, you solve for yourself. Next element, you solve for yourself, given what we know about this element now. Next element, you solve for yourself based upon what we know. And you go around and around and around these elements and solve until finally you converge down to a solution. So that's the basics of the analytic element method. And I've talked an awful lot. I talk fast. James, what can I re-explain or answer, or what kind of questions are out there?
All right, this is a pretty good overview question. It's the question is, AEM seems to handle a large variety of scenarios. Are there current limitations where AEM might not be as useful or practical to implement as numerical methods such as finite volume or finite element?
Yep, finite element, finite volume, finite differences, they all have their place. And in general, if you have a complicated problem, you will be able to solve the problem faster without the analytic element. The analytic element has these mathematical functions, and as you add more and more and more mathematical functions, your models run slower and slower and slower. So that's one limitation, is just in terms of the number, the degrees of freedoms that we can have in an analytic element method solution. If you have a particular problem, and for those of you that are water wave people, this is the wave equation. The wave equation is different than the mild slope equation. So if you're looking at something where the variability of the bathymetry is smooth, and that's important for your problem, then that is not conducive to an analytic element method solution. There are ways that we can take the solutions that we have and turn them into things that we can solve with the analytic element method. For example, I don't think I have any examples in the book to show this, but in the groundwater world, we assume that the base is constant. And I have a number of papers that analyze looking at stepping base instead of a sloping base. And I've shown that if the steps are small enough, and they don't have to be that small, but if the steps are small enough, you will get the exact same solution that you have with a sloping base model. So sometimes these things like of variable conductivity, if we have a field of conductivity that varies with some kind of a functional form, that may be important. And for problems like that, then a numerical solution would probably be what you would want to do. The analytic element method also, however, gives you a lot of insight in terms of the things that are important and are not important for your numerical solution. So there's a lot of insight that's gathered. And I can give you an example there. I worked with Professor Strock to develop quite a bit of the code for NAGRM, for the National Groundwater Model of the Netherlands. And that was all analytic element method. And that gave a lot of insight that was then used to develop a more detailed layered model with transients of using IMOD for the National Groundwater Model of the Netherlands. Sorry, that was a very long question to a very short, or a very long answer to a very short question.
Thanks, Dave. There's another question here regarding the phreatophytes. He's saying, for the tree example, how well do you need to know the characteristics of the subsurface, and how is the geometry of the network of tree roots taken into account?
Somebody's an eco-hydrologist out there. So I will tell you that let me see if I can get back to that one quickly. So this particular, when I put this together, Trevor Ehring and I worked on this one. Trevor is out in Groundwater Management District number 3 now in Southwest Kansas. He's their GIS modeler. And I didn't know, we had no way of knowing what the functional form was of the actual uptake by the tree. We knew that you know, we knew where a lot of trees existed for a lot of different types of trees. We know that cottonwood trees put down trees up to about 3 meters, about 10 feet. We know that they're kind of generally dispersed fairly evenly by the time you get to the water table. Some trees have more pronounced taproots. Some have spread their trees, their roots out like their branches up above. And so in this paper, I developed 3 different mathematical functions. This one shows the water uptake evenly over the entire canopy of the tree. I also developed a couple of mathematical functions that focused the extraction about the taproot with 2 different mathematical functions. And so This was something that had never been done before. These mathematical functions were the first time that I know of that anybody modeled that uptake. This here, I can tell you that this particular example, actually, I only backtraced 10% of the trees. If I would have backtraced all the path lines for all these trees, it would have completely filled this dark. So basically, the capture zone for this field of phreatophytes is the top of the water column right here. When this was an invited paper, and when I got this result on a Friday, the paper was due on Sunday, and I just couldn't believe it. It's like, this can't be right. I don't, how do you interpret it? And after thinking about it for a while, well, yes, of course, this has to be right. This has to be the way that the particles are going up and down. It just, physically it makes sense. So once again, a long answer to a short question. These mathematical functions satisfy mass balance. The mathematical functions satisfy mass balance to the computer accuracy of the computer. So you've got 16 digits of accuracy for the mass balance. It uses the quasi-linear approximation of two-dimensional flow to get the three-dimensional streamlines. But that is valid for problems that are diffuse in nature. And so it's a solution. Now, how well this matches reality, I think maybe that's what the question was getting at. This will give you some insight so that you can understand what's going on in reality. In reality, there's probably other drivers in the soil column that are perhaps creating a lot of intricacies and complexity there as well. One of the things, and I wrote this book so other people can use the analytic element method and develop their solutions. And one of the things that I've thought about doing, I never have, but you could look at the hydraulic lift of the water being brought up by the tree. So the tree pulls hard during the daytime and respires at night and lets the flow go back out into the soil column. So there's kind of a diurnal pattern of water going in and out of the roots. And so there's a lot of complexity. I don't know that I answered the question. Maybe I danced around it.
Yeah, there was a little bit more subtlety about how do you actually parameterize the trees, I think, but I think you got the core of it.
Yeah, so the water balances, we got that. There's lots of papers published on recharge. So we at least know what the bounds are of recharge from published articles in this part of Kansas. We know that, it ranges between 1/4 and a couple inches per year, depending upon the types of soils you have up above. And these trees, there were some studies that were done using to measure the sap flow to figure out how much water is going up in the plant itself. And there are also some isotope analysis done of that water to be able to differentiate how much of it is coming from the soil and how much of it is coming from deeper in the groundwater. And so we used that information to be able to come up with our estimates of kind of overall how much water is being brought up by the tree from groundwater sources.
All right. There is one more question, which you may or may not want to address now, is how do we compare the analytic element method with the boundary element method?
Do we have a boundary element person out there? Is there a boundary element person out there?
I suspect so, or somebody
Okay.
who knows enough about the boundary element method to be dangerous.
So the boundary element field has probably advanced well beyond my understanding of when I've looked at that in the past. The boundary element, the primary difference to my knowledge, and I suspect it's probably come a long ways since this, but if you look at some of the early books on boundary element method, instead of using a mathematical function to model this, it would use Gaussian quadrature to do the integration numerically. And there's not a need to do that. The mathematics for these double layers and single layers are all out there in the book. The mathematics for these elements all follow Muskelishvili, and actually which forms a basis for the boundary element as well. And so, and once again, I'm dancing around the answer, but do you have any other questions at this point, James? And we can maybe open it up to some more general Q&A at the end too.
Yeah, that's the only one for now.
Okay, very good. Based upon my response, if you'd like to continue this conversation, I'd be delighted to do that shortly. The last thing I wanted to do, so I wanted to kind of introduce you to the kind of things that we can do with analytic element method, the kind of problems that we can address, the simplicity of the formulation. The complexity gets in the formulation of the mathematics, but once you do that, it's done. And then it becomes kind of an elegant solution of bringing things together. The last thing I wanted to show you, and I showed you the book, I showed you the kind of things that are in the book. The last thing I wanted to show you was some examples. And I'm going to go to scilab.org. And Scilab is essentially an open source MATLAB. I used to teach all my courses using MATLAB, and I wrote code with students using MATLAB. About a dozen years ago, a colleague from France, Philippe Legrand, came and visited me for a couple of weeks, and he said, "Hey, Dave, you should really look at Scilab. INRAE in France has developed this new tool, and you may be able to use it in your course." And so I looked at it, and it's really a nice software tool to be able to analyze engineering and mathematical problems. And you can download it right here. It's open source, it's free. I like it because once I've taken students through a set of exercises and we write code together, they can use that code forever. Once they leave the classroom, the code that they wrote in classrooms however long ago what it was still will run on Scilab. And I have a set of examples. This is the zip file that's out there. And let me just show you this one right here. So this is just some Scilab code. If you download Scilab, you'll be able to run all of these examples that I have out there. And so you can see that the interface looks very similar to MATLAB. Let me just run this one so you can see it. And so this is the example that I showed you of the three wells with the streamlines, and the particular mathematics for this is simple. This is all the code right here, Q over 2 pi log Z minus the location of the well. So it's the complex version of the team solution. There's 3 wells, so there's 3 team solutions. Let me show you one more example, and then I'll take you a little bit more into kind of how the code is organized. So I'll take you to a little bit more complicated example, and let me go down here to this one here. And I'm just running this on a laptop. So I'll start running, and then I'll take you through the code as it's running. This one takes about a minute to run. At the top is kind of the boilerplate. This is all open source. I've got the Creative Commons attribute at the top of every one of these. This particular one has, every one of them calls this visualize code. All that does is makes the pretty pictures, the greens and the drawing the lines and so forth, doing the contours. So it makes the pretty pictures. This particular type of problem, the boundary condition is a potential specified. There's a uniform flow component where we can specify the known elevation of the known potentials at a set of points. We have a complex potential for that, a vector field for that. We've got a solve algorithm to solve for the coefficients, and then a algorithm here to compute the error, the residual error. I'll show you a little bit more about that in just a second. The second type of element is a slit element. So this is, here you can specify the endpoints, the type of solution we're specifying a given potential, the value of the potential that we're trying to solve for. It sets up the different things that are required in a list structure for that slit. This is omega. This is just nothing more than coefficient times z to the minus n power in a transformed domain. So this is the function that's straight out of the book. This is the complex vector field. And so this equation comes straight out of the book, coefficient times a function. These are the additional functions that I was talking about in chapter 2. This is the solve algorithm. So this solves for the coefficients using that A matrix and the given potential that we have right here. So that's our F function, that's our A. This is our coefficient. We compute the error at the end. So the residual error is nothing more than the computed potential minus the specified. Let me get out of here for a second. Minus the specified potential. Then we take it across all the elements and develop a root mean squared error or an absolute error and show the results there. And then it can draw. Here we specify the endpoints, we specify the uniform flow, we specify the set. This is all out there so you can take a look at it later. Specify the nodes, specify how the slits are connected. We iterate through a number of times till we get a small solution. We show the error, and then we compute the potential of the vector field and draw it. This is the result that we get. So here's our stream network with increase in potential along each of the stream reaches. It iterates through all the elements solved for themselves. It took 524 times of solving everybody for themselves to get a residual error where the change in potential across all controlling points of all elements was we had 10 to the minus 12 accuracy. Here's the root mean square error for every element. The root mean square error is 10 to the minus 5 for everything. We have a difference in head of a potential of about 10. So our normalized root mean square error gives us about six significant digits of accuracy. And there's a number of other solutions out there you can go ahead and take a look at. You know, they're all there. They're organized the same way. You specify the element, you have the computation of the complex potential or the potential and the vector field. You solve for it, you draw it, and so it's all organized around the same basic architecture. And that's as far as I thought I'd be able to get you today, James. Thanks everybody for your attention, and I'd be delighted to take any other questions or have discussion as you see fit.
All right, so I guess we'll open it up to questions, general questions, specific questions. Feel free to throw them in the question and answer box.
As you're thinking, I'll just kind of take a step back and say that this is something that I've been working on for a long time. I've been studying the analytic element method for a little over 30 years. And I also should have apologized up front. I come from Minnesota originally. I'm at North Dakota now, but I come from Minnesota. Actually, North Dakotans talk about the same as Minnesotans too, but we talk fast. We have to talk fast to get our words out before they freeze. So apologize if I'm talking too fast for you.
No worries. I don't see any other questions here. So given that, I think we'll probably close up. We got 4 minutes left in the hour, so that's appropriate. Thank you very much, David, for your presentation today. Really enjoyed it. It's really neat to see some of the stuff you're doing with the extension of the analytic element method to waves and some other fields that we have not been working in before. So really great stuff. And we have some thanks in the Q&A area as well. So thank you, David, for your presentation.
Thank you. And I would just encourage you too also that I wrote the book to try to make it simple. And, you know, I would just encourage you, if you have some interest in this, to at least take a look at the part that's out there for free and see whether it's something that you might be able to utilize. And I'm really hoping that we can develop a broader understanding of the kind of things we can do with AEM techniques in the science and engineering discipline. So thank you very much for the opportunity to be able to present to this group.
Thank you. And I think we'll probably close down here. Dave, we should catch up